Okay, now we're ready for cross products of vectors. This actually uses something that we did in matrices. Now, we mentioned before there are two types of multiplying vectors. There are dot products and cross products. We already did the dot product. When we did a dot product, we ended up with just a scalar, just a number for an answer. Well, when you do a cross product, you end up with a vector for an answer. So if you see this with the x in the middle, that's called u cross v. So the other one's called u dot v. This one is called u cross v. If we want to find a cross product, what we're going to do is we're going to set up a matrix. The top row we're going to just call ijk every time, ijk. Then the two vectors, we're going to put those components as the other two rows. So here's vector u, its three components are the u's. Vector v, its three components are the v's. So you set up this. Now if you remember this from matrices, we start off with the I, then we take these four right here and cross multiply and subtract. So that's what it's saying here. u2 times v3 minus u3 times v2. So that goes with I. Then it's always minus the second one. Now we move over to j. Now we're going to do the outside four. So again, cross multiply and subtract. So u1 times v3 minus u3 times v1. Then plus, we move over to the last one, which is k. Now we're going to do these four in the lower left. So u1 v3, or v2, sorry, u1 v2 minus u2 v1. So it's the exact same thing when we're finding the determinant of a 3 by 3. Except the top ones you're going to have letters instead of numbers every time. So if we had these two vectors, u is 6, 2, 1, v is 1, 3, negative 2. The first thing is to set up our matrix. So remember the top row is ijk. Then you can put either one of the vectors and it doesn't matter next. So if I put u next, that's 6, 2, 1. V is 1, 3, negative 2. Again, so there's our setup. Now, again, for I, we're going to cross multiply these lower four. Cross multiply and subtract. So to write that out, that's going to be 2 times negative 2 minus 1 times 3. So that's going to be our I. Minus, now for j, we're going to do the outside 4. So that is 6 times negative 2 minus 1 times 1. That's our j. It's always minus that middle one. Then it's plus. For k, we're going to do the 4 on the lower left. So that's 6 times 3 minus 2 times 1. And that's our k. So hopefully you remember doing this last week in matrices. Now to simplify them, let's see, that's negative 4 minus 3. So that would be a negative 7i. Here, that's a negative 12 minus 1. So that's a negative 13. Now it's minus a negative 13. So that's plus 13j. Here, that's going to be 18 minus 2. So that's 16 plus 16k. So that's u cross v. Now that's in ijk form. If you just want it in component form, we just take the coefficients, negative 7, 13, and 16. That would be the component form. Now some uses for this cross product. One, it's a nice way to find the area of a parallelogram. The area of a parallelogram, you just take u cross v and then find the magnitude. That should have second. Change it. That should be magnitude there. Well, the area of a parallelogram, we're just going to do that with this. We're going to say, okay, let's set that up. So again, our first row is ijk. These are the two vectors from one corner. So if you think of a parallelogram, as looks like this, it's a bad parallelogram. So like this would be u, this would be v. So if we just know those two vectors, we can find the area of that parallelogram. So ijk, we have 2, 2, negative 3. We have 0, 2, 3. So if we work that out, let's see, for I, we're going to do the lower 4. So 2 times 3 minus negative 3 times 2. That's our I. Minus, for j, it's the outside 4. So 2 times 3 minus 0 times negative 3. That's our j. And then for k, it's the lower left. So 2 times 2 minus 2 times 0 for k. So let's see, that is 6 minus a negative 6. So that's 6 plus 6. So that's 12i. This is going to be 6 minus 0, so minus 6j. And that's going to be 4 minus 0. So that'd be plus 4k. So that's our cross product. Now we want the magnitude of that. So remember, for our magnitude, we take the square root of 12 squared plus negative 6 squared plus 4 squared. So that'd be 144 plus 36 plus 16. So that would be 180 plus 16 is the square root of 196, which actually turns out to be 14. So here, the area of that parallelogram is 14. If we had done the same thing, let's say this was a triangle, and I knew this side was U and V. We could use this for an area of a triangle, because a triangle is actually half of a parallelogram. So if this was a triangle with those same two vectors for U and V, we'd take half of 14, and our area would be 7. So if you're given the vectors that form one corner of a triangle, you just take the cross product, find the magnitude, whatever you get, take half of it. Now the last thing is called a triple scalar product. It's quite the name of something. A triple scalar product. A triple scalar product is U dot V cross W. So it contains a cross product for V cross W and a dot product because you're taking U dot that cross product. So it's a combination of both of those. Now that looks like a lot of work. It's actually not too bad. This is really exactly like what we did with matrices. Because what you do, your top row that was ijk, now this vector that's on the outside, the one that we're dotting, becomes your top row. So if I gave you these three vectors and said, find the triple scalar product, we'd pick one of them and put it on the top row. So here, if it's U dot V cross W, let's put U on the top. So the top becomes 2, 3, 1. Let's put V on the bottom. Well, it's got one I. It's got a negative 1j, but it doesn't have a k, so let's let k be 0. And then W is 4i, negative 3j, 1k. So it's just like what we did, except now the top row is numbers instead of ijk. So this is just like we did with matrices. So we're going to take 2 times, remember the lower right, we're going to take negative 1 times 1 minus 0 times negative 3. Minus, then we're going to have a 3 times the outside 4, so that's 1 times 1 minus 0 times 4. Then it's plus the last one, 1 times the lower left, that's 1 times negative 3 minus negative 1 times 4. So see, that's negative 1 minus 0 is negative 1. 2 times negative 1 is negative 2. This one is 1 minus 0 is 1. Negative 3 times 1 is minus 3. Here, that's a negative 3 plus 4. Can't read my writing for that's 1. So plus 1. So the triple scalar product is negative 4. Now this can be used to find the volume. I'm sure you deal with this a lot. The volume of a parallelepiped. A parallelepiped, it shows up sometimes in chemistry. Some crystals, if you've ever seen crystals form, they are formed in different three-dimensional shapes. Well, one of them, sometimes they form a shape that is a parallelepiped. It also, some compounds form in the shape of a parallelepiped. I think of a parallelepiped as if I took a box, a regular six-sided box, and I put my hands on the opposite corners of that box, and this box was very flexible, so I could squeeze the opposite corners together so that every side of the box bent and became a parallelogram. All six sides became a parallelogram. That is a parallelepiped. You'll probably never run into that, but that is a triple scalar product. Okay, that's it for that.